Okay. Today, let us begin with actually proving the Cauchy mean value theorem, right? Because we have not proved it yet, and it will be fundamental. So, proof of the Cauchy mean value theorem, because we have used the Cauchy mean value theorem as a motivator to learn other things, parametrizations and polynomial parametrizations and such. But we never really discussed the proof of this. So let's actually do this, okay? Proof of Cauchy mean value theorem. So today I'll just state it very plainly because we have seen how it comes about in trying to generalize. So it is like we have the Lagrange mean value theorem, right? And we try to generalize it for curves other than just graphs of functions. And that leads to a kind of statement that we predict geometrically, then we state it in the form of equations, and we get the Cauchy mean value theorem that it should be true, but that's sort of proof, and then we prove it. So that's what we'll do, the proof part. So let us do the statement. And I think if some of you have done the proof, then we can see. Because this will, this basically tells us the relation, right, between slopes and derivatives. And so it will be very useful soon when we do Taylor's theorem. It will be useful to prove other kinds of things, you know, like L'Hopital's rule and many other things. Sorry, not sharing my screen. But anyway, still now I have not. I did write a few things and so on, but anyways, now should be visible. Okay. So yeah, so it will be useful for all. Let's actually prove this. Okay, so let us give the statement quickly. So let's say that. So 1 minute. Yeah, and then we will also be proving this for more than two functions at a time and so on. But that we'll do later. So let's do this. So given f and g, and they are both functions from a comma b to something, some r, and both are differentiable. Okay. Differentiable. So today I'm just to say it again. Today I'm just going to prove this. We're not going to talk about the theorem because we've already done that. So we're just going to do the proof. Okay, and demonstrate the thing directly. So differentiable, and then for any x naught comma x1, there exists a c, obviously depending on x0 and x1, such that the slope of the curve, so you know what curve this is, this entire thing, this f of x0 minus f of x1 by this thing, this entire thing is the slope of something. That's something we have seen. This is equal to, obviously, we don't need to know that it's the slope of something for the proof or even for the statement, nothing like that. But that was just why it is geometrically evident. But we saw that earlier. So there is one C that works. That is the magic. There is one C that works here. Okay. So today we really want to just prove it formally as it is done in usual. Okay. Yeah. So how to prove it? So proof. Let's think about this. Okay. Sorry, can you be louder? Yes, yes, certainly. That is correct. There should be. No, actually, that condition is not needed in some sense, right? Because if gx naught is equal to gx1, so obviously, in some sense, you are correct. But if gx naught, but but I'm also correct in the sense that it's really not needed. If gx naught is equal to gx1, then what can we say? Then we can say that there exists a C such that G dash C is 0, right? So then this side also becomes infinity. There is an exception, but other than that, this also becomes infinity. And this also becomes infinity. Well, again, there is an exception. If this is also 0, then that's a different there. Okay. Otherwise, both sides are infinity. Okay. Otherwise, both sides are 0 by 0 or something like that. So yeah, so, but yes, if because we are not considering infinity as a number, if we are not considering infinity as a number, then I must say that, yeah, gx naught is. Otherwise, yeah. Yes. Sorry, what start thing? Oh, yes, 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 sure, sure. So today, so I just said that today we are going to do the proof of the Cauchy mean value theorem. We have seen how the Cauchy mean value theorem comes as a generalization of Lagrange mean value theorem. Okay, so just to put it in one phrase, you see, all these mean value theorems are basically geometrically evident facts. Like the Rolle's theorem, there must be a horizontal tangent. That's the geometrically evident, super evident fact. If we just draw the picture, it must be true. Similarly, the Lagrange mean value theorem is also a geometrically evident fact. But the Lagrange mean value theorem only holds for graphs of functions. Right? I cannot just draw anything, even if it's a nice, smooth thing. For this, Lagrange mean value theorem will not be true because this piece of geometry that I've drawn is not the graph of any function, right? But if we try to extend the Lagrange mean value theorem for graphs, for other curves other than graphs of functions, then we get this Cauchy mean value theorem. And we had discussed how we do that. So I'm not, because we're not going to do that again otherwise. Okay, that we did long time back. But yeah, point is that generalizing that brings us to Cauchy mean value theorem. Symbolically, also you can see there are two functions in place of one. So today we have seen the motivation again. So we know that the Cauchy mean value theorem ought to be true, but we have not yet proved it. Okay, and the proof is very important because a similar method works in proving a lot of other similar there exists a C kind of statement. So that's all. And I also said that basically, this will be used to prove Taylor's theorem, L'Hopital's rule, and many other things. So we will. Okay. That's it. And so then this is the statement. Statement is just here. For any x0 and x1 you take, this ratio, that is the behavior of f and g, is actually captured by the derivative. This is again in the same spirit as other mean value theorems, right? So there is a point C in between, which is kind of a mean, right, which captures the slope. So this is the slope of this following curve, right? But that is not needed for us now. If you take this function from R to R2, then this is the slope of that. But let's not get into that. That's not needed for the proof, so we'll not. That's all. And the main thing here for this theorem to notice is that there is one C that works. If there were, if that restriction was not there, then it is very simple to prove using Lagrange mean value theorem and dividing two equations. Okay, let's think about this. How do we prove this? Okay. Into gx minus gx1. So this is all into all. Fx minus fx1. Okay. Okay, apply Rolle's theorem. Okay, so I think this will work. Okay, so that is just some details that have to be worked out, so that's fine. But if I ask you this question, like, how did you come up with this function? Mm-hmm. Okay, okay. So reverse engineering. Okay, okay. This will certainly work. Yeah. So you have constructed a function. This will certainly work. Okay. Let me do it. We'll end up considering the same constructing the same function, I think. But let me do it in a way. So I will give a proof which will be the exact same that we had used to prove the Lagrange mean value theorem. Okay. So exact same method. And this is a very widely used method, we'll see. Exact same method as LMBT. So what is that? Right. So yeah, the idea is to basically again reduce it to Rolle's theorem. Reduce to, that is the idea. So what I'll be doing is first I'll just make it without any fractions. So basically I'm also kind of doing reverse. Is equal to 0. Now you see, what kind of statement does Rolle's theorem prove? So this is just equivalent, more or less. What kind of statement does Rolle's theorem prove? Rolle's theorem kind of gives us that there is a point where the derivative is 0. That's the kind of statement Rolle's theorem gives us, right? So if we want to apply the Rolle's theorem, and this is a technique that's used in hundreds of problems, okay? So because we want to apply the Rolle's theorem, we would like to view this thing as the derivative of some function at C for some function C. Okay, so we would like to view the LHS as the derivative of some function at C. Okay, so it will be a function of C. Then we can hopefully apply the Rolle's theorem. Right? And what that function is, basically you have to take the antiderivative of this, right? This expression where this quantity is a constant and this quantity is a constant. Only this is varying. The C is the varying. If you take the antiderivative of this, then what function do you get? If you take the antiderivative, then you basically get, and that will exactly be, I think, what Rastov also said, right? If you take the antiderivative, so again, I mean, we don't have to prove anything while doing this. We can just say consider this function, but this is how we construct that function. That's all. Okay, this is certainly the antiderivative, right? And the derivative of this at C, obviously, then will be the LHS. Now, again, I'll say the same thing, apply Rolle's theorem. Let's actually check it. What is G of X naught? So it is f of X naught. Let's actually compute it. F of X naught times G of X naught minus G of X naught, F of X naught, G of X naught, plus this is what we get. Does anything cancel? No, right? This is what we get. Now let us apply it for x equal to x1. Hopefully we should get the same point. Okay. So my function, I think maybe is a little simpler. Okay. But yeah, some of us are already expert at this tech. Okay, I didn't mean to do this. But let's do it. This g of x1. Let's see if we get the same thing. I hope we get. So now I'm putting x1, and please cross check with this. Either you can just see this and check, or you can work it out yourself and check also. So let's expand it. No need to. Right. And then we have f of x1, g of x1. Wait, but this term we don't get, right? No, we do get. So there is some problem, right? In my note, in my thing, in my working here, right? No, there's no problem. Okay, so let's continue doing this. So we have let's continue this, see what happens. Yeah, so are these things the same? Can anybody check it? The same, right? But where is f of x1, g of x1? Wait, this cancels out. They get crossed out, right? And so here also something gets crossed out. Yeah, obviously it should, yeah, by symmetry and so on. Right, I'm just, yeah, okay. So now you see, right? So it works. So g of x0 is equal to g of x1, and hence there must be a c such that this happens, and then you can just turn it back and do, okay? This method is very powerful, okay? It's just reducing what you need to prove to proving that the derivative at some point is 0. Okay, so give me 1 minute. This was probably a little boring, but I have to do these things. These are the standard theorems. So yeah, now let's just jump to something little non-standard. Okay. Yeah, let's see this problem. So last time we were looking at some things like this. Okay, given a set S, let's say in R3. Okay, so we had seen some set, I don't remember exactly, but something like this, sin x comma cos x, where x is from 0 to pi, whatever. Just want to, keep it a little interesting. We had seen this kind of, this is a subset. Let's say this is the S. So this is like S is given as a parametrization, right? So S is what? S is the image of a parametrization, right? S has a very obvious parametrization from 0 to 2 pi to S, the obvious function, which is just this function, right? That x goes to x comma sin x comma cos x. Right? So we had seen the S is basically a set which is the image of a parametrization. Okay, S will be some complicated thing in R3, but we have seen it as a parametrization. Obviously, it has 3 functions in it, so we don't exactly know how to apply the mean value theorem. But for example, if there are only 2 functions, sin x and cos x, then you could apply it. Right? You would just basically get the circle, and yeah. But then we asked, this question, interesting question, that can S be written, so is there a polynomial? Is there a 3-degree polynomial such that its set of roots is equal to S, right? So is S describable using a polynomial? Obviously, 3-variable polynomials. Is there a 3-variable polynomial whose roots are x, sin x, and cos x, right? For all x. And we had seen the answer is no. We did some arguments. Today, I want to ask a similar question, but for a different set. So let's see. And all these have a lot of significance, like actual meaning, but for us, it's basically just a game, more or less. Okay. But also we are making some observations and such. So we're just going to do a similar problem. Okay. So here is your set. So your set now lives in 4 dimensions. Okay. But that is not a problem. We have x cube, x square y, x y, wait, yeah, xy square. X and y can be anything, R in R. Yeah. No. It was in 0 to 2 pi. Try to recall the problem. So first I had given in R, but then I realized that I should give it in 0 to 2 pi. So I changed the question. Yes, I think you had also asked me, is it in 0 to 2 pi or R? And I said it was in 0 to 2 pi. Yeah. But for R also, even if you take it in R, still there is no polynomial. But that I think is a little more difficult to prove, which you can try. But I'm not asking you to try because I don't know. It can be very difficult, so it might be out of the scope. Okay, but still you can try. Okay, and the answer will be again no. Okay. But yeah, I'm trying to give things which are in the scope. So it's okay. Yeah. So here we have this. Now again, this can be looked at again as a So you have a parametrization done by 2 things, x comma y, going to this, and S is the image. S is the curve which is parameterized like this. Okay, there are 2 components. One may be angle, one may be distance, whatever. I mean, actually, this has a very big meaning. This is the projective line, and this is the projective plane. Inside the projective plane, you're trying to view the line inside the plane in some twisted way. But anyways, those we don't need to go in. We don't need to know how the problem is coming. We just need to try to solve it for now. So yeah, this is what. So again, S is a set in R4. We don't need to see it. Okay, but it's a set in R4, which comes out of a parametrization, the image of this function. But our question again is, are there some polynomials, some 4-variable polynomials now? Okay, some 4-variable polynomials. Maybe I don't know how many, F1, but I will guide ourselves in strategy of this kind of how to do this kind of question. Okay, F1, F2, F3, I don't know how many, such that the set of common zeros, the set of common roots of all of them is exactly S. Okay, so what I'm trying to say is that but the way to solve it is very practical. This looks like a very strange question, though it might still look like should look like an interesting question, but it's a very strange, like unapproachable. But we'll see. There's a practical way to set up things. It's like a question in elimination. You want to eliminate and get relations between things. We'll see. So this is S. 1 minute. Yeah. Second, yeah. We want to see if there are things such that the common zeros, such that x0, x1, x2, x3, such that f1 of, so the common zeros of these f, let's say assume I'm just asking for 3 polynomials. Okay, we can keep it like that. Such that the common zeros of these 3 polynomials is exactly this set. Okay. And once again, these parametrizations mean that we'll see. Okay. This parameterization means that you can again apply the Cauchy Mean Value theorem to this curve. But that's a little later because it's in 4 dimensions. Yes. So this is basically the question. Okay. Are there 3 polynomial? Are there 3 equations? Are there 3 equations which, when you solve, the answers to those the answers, right? The solutions are exactly like this. Okay. So what you should do, okay, first take a minute and absorb the question. Then we can think how to approach. You can think and see. Okay. 1 minute. 75. So what you have to really do is, you see, there are four things here, right? You need to just set up equations between these 4 expressions. Isn't that right? Yeah. There are these 4 expressions, and you need to find relations between these 4 things. That's the way you will get equations, right? And those equations, the solutions will be these things, these kind of things. So that is just how you have to do it. Otherwise, how will you no, yes or no? That's difficult. And you see, these are actually very special. Okay, these are all all possible monomials whose degree is 3. So even for degree n, when there will be n plus 1 monomials, that also can be described using equations. Okay. And by the way, if some set can be described using equations, then that set really becomes very special, right? It means then that set really has meaning. That set is the set of, because the equations are like sentences, right? So it means that set is really are really the truths. It's like a truth table and the set of values for which those sentences become true. So it really makes those sets special. Those are called algebraic sets because they are defined through algebraic equations. So remember, we want these to be algebraic, meaning that basically we want them to be polynomial is what I mean. No square roots, no sin x, cos x. And you won't even think of that because it's just all algebraic, simple monomials. So yeah, we just want to find relations between these things, these expressions, and set up the equations, and then see if they are enough. If not, then we add more equations, and soon we will narrow down to S. Because the more equations you add, right, the set S becomes smaller. Is that right? The more equations you add, the common solution, right? So S becomes smaller and smaller. So come on, so there are these four expressions. If I just give you these four expressions, just these four things floating around, how do you find relation between them? One more minute. Yes, exactly. So that's one of them. Yeah. I'll just write it 1 second. So these are the kind of things we are trying to say, right? So that means that for this polynomial, so if I say the polynomial is x naught, so remember, in the solution, this should correspond to x cubed, this should correspond to x square y, and so on, right? So x naught, so one of my polynomials should obviously be x naught, x3 minus x2, x1, x1, x2, I should just say. This is my f1. Why not? Right? Because if you look at the if you look at f1, then f1 of s is 0. Obviously, f1 has there are other values where f1 becomes 0, which is outside s. Is that right? Yeah, f1 will become 0 for other things also, but f1 of s is obviously 0 because that's how you've done it. That's how you've created. Yes, yes. Oh, sorry. Yes, no, but then that will not give you any new solutions. So what's the need of this? If you give, yeah, right. So that's a redundant polynomial. So we don't want this. Okay, but yeah, okay. But the problem right now is, but the set of roots of F1 is a strict superset of S. So we need to add one more condition or one more equation maybe, or two more, I don't know, such that we end up with exactly S. So there are more relations, right? Already Raghav has given us one way. So now it should not be hard to find other such things because now the ball is rolling, right? Some other relations between these things. No relations. These are some four simple monomials, right? There should be more relations between them. Just try out all possibilities, right? Just try to square the second one and see if you can create it in some other using the other three, or try to square the third one and do it, or just something else, you know. Okay, let's try that. If we add the first two and divide, so this is the problem with this is not a polynomial, but yeah, but this we can still manage to make it from here something that. Then what? Uh, but where is the relation? There should be some relation. That's right, but that's right. Yeah, but yeah, right. So xy. Uh, yeah, but then the point now is that you need to again be able to write this in terms of these four things. Then only you will get a relation. So yeah, let's try it. So we have x by y minus 1. Now minus 1 is y by x. No, I don't know. I don't know. I don't think this will work. But there are some very simple options, right? Yeah, all of them have degree 3 only, right? So what are the possible relations? If you have x square y, you just try to square this, just play around with it. You get y square. So how can you get this expression? Obviously, you can get it again, right? You can get it by x cube and xy square. Yeah, everybody agrees with that, right? So then we can add this. Yeah, we can add this equation. So the way I will say it is, yes. x1 square, yeah, minus x0 into x2. Perfect. No, not x2, not x2 square. Okay, let's try it. X2 square minus x1 into x. Does this work? Yeah. Oh, this works, right? This works. So you get these three equations now. Wow. Okay. So once again, you see that these three equations all vanish at s. Okay, f1 of s equal f2 of s equal f3 of s. But is the common solutions exactly s or more than s? That you have to decide. That you have to. That's the left, right? So if I want to write it in a formal way. So you see how these polynomials are created, right? Is just adding the relations, setting up equations between these things. Using symmetry, argue something, degree, homogeneous, and so on. So we see that the common solutions of f1, f2, f3. So certainly we know till here that this is true. So for homework, show that equality holds, and this is not difficult. So try to show that given these three equations, the only solutions that you can get. So basically, you have to just solve the three equations simultaneously. This is some tricks you have to use, right? So you have to show that the solutions can be, any solution you get will be of this form. Okay, so I mean the solutions could be 1, 1, 1, 1 also, but that's also of this form for some x and y, x equal to y equal to 1. Yes? Yeah, so these are 4 variables, right? I mean, yeah, we are not using the 4th variable, but yes, that's right. It's a polynomial in 3 variables, but also you could say it's a polynomial in 4 variables where the 4th variable does not feature in. That is fine, right? It is okay. I mean, it can be seen as a polynomial in 4 variables. Right? Yeah. Mm-hmm. One of? Why should we assume that? No. But the fourth variable is not 0 in all three. Right. Here the fourth variable is there. Right. So yeah, that's a good point. I mean, if you ask for the set of zeros for this for only f2, then you will see something like this will be true. We can say 1, 1, 1, and in place of the fourth variable, you can actually put anything. You can put pi also. You are right. This will be a solution. The fourth variable can be anything, but that is when you are only considering f2. That is why we have to consider all three and we have to take the common solution. So when you take the common solution, then the fourth variable cannot be random because it will be constrained. If you try to solve it, you will see x3 will have some, x3 is in terms of other three, right? So it's already constrained. Yeah. So the first polynomial will will restrict the fourth variable from being anything. Okay. Yeah. Try solving it and you will see that the common solution will be exactly as. So this is the first thing we want to do. The first thing you have to do. 1 minute. So yeah, this is what the first thing you have to do. And then show, and this is also an interesting exercise. Okay. Show that for any two of f1, f2, or f3, if you take any two of them, then it does not work. Any two of f1, f2, f3, the set of common solutions is strictly bigger than S. And this is also not difficult, but it's a little interesting because for a second I used to think that two of them are enough. And you'll see if you try solving it, you'll see it's interesting. Okay. So these are the two things I wanted to ask. And just give me one more second. Let me think if there are some other interesting things I can say. So we have, and we will see how these things will come into play, but we'll have to do more practice of these kind of things. But 1 minute. So this is 4 and the solution is 3, 2, 1. 1 minute. Huh? So then you become, 1 second. Yeah, anyways, leave it. Okay. There is actually something more is true. Okay. That is, if you, so we have written this set S as the set of, once you show the first part, especially, then you will see that the set of common solutions of this is equal, right? So we have found 3 polynomials for which this is S. It can actually be shown that you cannot, so there are no 2 polynomials which will work. Not just among this, but it's like, you cannot be like, at this point, there is still a scope that some smart guy can come in and give me 2 polynomials such that the common 0 becomes S. That's possible, right? We have not shown that. We have not shown it is not possible, right? Even after you show these two things, it is still a possibility, right? That there are some 2 polynomials lying, some very complicated polynomials which you cannot think of, and its common solutions will be S, exactly S. But actually, there are no 2 such polynomials. Like it's not possible to find. But that is incredibly difficult to prove. Okay, yeah. And actually, intuitively, 2 polynomials should have been enough. That is another strange thing here, right? But I don't know how to explain that because think about it like this. You have a polynomial in 4 variables. You have a polynomial in 4 variables, right? So there are 4 degrees of freedom. If you take the common solutions of one polynomial, so you start with 4 degrees of freedom, right? If you take the common solutions of one polynomial, then that should ideally have 3 degrees of freedom, right? If you write an equation in 2 variables, linear equation in 2 variables, it's a line, which is 1 degree of freedom. So 2 to 1, right? Similarly, four variables, after you solve, the set of solutions should be 2 degrees of freedom. So 3 degrees of freedom. Once you have another polynomial, you cut it with another polynomial, common intersection, it should become 2 degrees, right? It should become 2 degrees of freedom. Yeah, that is where, because this was initially in some other language, I'm trying to translate it. It becomes 2 degrees of freedom. And yeah, and if you think about it, yes, exactly. This set is like 2 degrees of freedom, isn't it? I mean, this set is like 2-dimensional, right? It has 2 degrees of freedom. So 2 equations should be enough. But there is something about this equation, it has some sort of a singularity at some points. That's a little difficult to say now, which demands one more equation. And this one more equation actually only helps to remove one more point from the solutions. So those are things which you will see once you try to solve it. So it's a little strange example, and it's a very useful one. Yes. Yes. So the idea usually, let me say it in a different way. So, or maybe I'll keep this here. My point is that I can show that in a very simple, using planes and hyperplanes and such things, instead of this polynomial stuff. Oh, yeah. You see, so let's consider R3. Okay. You see, R3 has 3 degrees of freedom. There are 3 coordinates. Every point, for the location of any point, you need 3 pieces of information, and so on and so on. 3 degrees of freedom. Now, if you add an equation in R3, let's take a very simple equation. Let's take x plus y plus z equal to 0. This object that you get, or the set that you get, which is solutions of this polynomial in 3 variables, right? The set of solutions for this polynomial in variables is 2-dimensional. So this was 3, right? But once you put this equation, you get a 2-dimensional thing. And what is that? That's just a plane, right? It's a plane. This is the equation of a plane, which is perpendicular to the diagonal of the rectangle of the square placed at the place like this. This one, and you have to do like this, and take this diagonal, right? And perpendicular to this, you get a plane, and that's basically this, right? That's a 2-dimensional thing, right? A plane is a 2-dimensional thing. So my point is that when you add an equation, the degrees of freedom reduces, right? You add the whole space R cube. When you add an equation, it becomes 2 degrees. It becomes 2-dimensional, right? That's the nature of it, right? Because it's basically, you can see that Z can be written in terms of X and Y. So basically it becomes, the third coordinate is determined by the first 2. And geometrically, you can see it's just a plane, which is 2-dimensional. When you add one more equation, add more or less any equation, right? You can add something like this, let's say. What will it become? Basically, you take another plane and cut this plane. You cut this plane by some other plane, some rotated plane, right? So you get some other plane, and you take the intersection of the 2 planes. What do you get? You get a line which is 1-dimensional. So the more equations you add, obviously there are exceptions to these things, but which can be categorized, is they are not surprises and such. One can explain why those exceptions come and so on. But if you actually take different planes in different directions, then the degrees of freedom should reduce, right? And you get 1-dimensional object. A line is just one dimensional, right? You can describe it with one parameter, just time, and that's all. You can just say the line. That you can parameterize it one thing. That is my point. So if you want some set which is parameterized by one thing, like t going to some now some complicated thing. Let's say you take something like t cube, t square, and t. Okay, now this is in 3 dimensions, but it's a one-dimensional thing. It has only 1 degree of freedom. So ideally speaking, if it has 1 degree of freedom, then you should be able to start with 2 polynomials and 3 variables and get here, right? One polynomial will reduce the degree by, now you will not get this set. It's not a line, so you will not get this one-dimensional set using planes and linear equations. You have to think of some complicated, but that's fine. You should be able to. Well, it should be possible, right? Yeah. You can, again, you have to just find relations between these things. It's simple. This is a very simple example. Again, you can actually find out the 2 polynomials. So ideally, 2 polynomials should be enough, right? You take one polynomial, the degree comes down, it becomes a surface kind of thing. You add another polynomial, another surface, intersect the 2 surfaces, you get sort of this one-dimensional object. So 2 polynomials should be enough to get this one-dimensional thing. Now, if you look at it here, right, you have a 4-dimensional thing. If I take one polynomial, I get a 3-dimensional thing. If I take another polynomial, I get a 2-dimensional thing. But this, sorry, I was saying this is a 2-dimensional thing. This set is a 2-dimensional thing, right? It's in 4 dimensions, but it is a 2-dimensional thing. It is the image of a 2-dimensional object. The dimension cannot increase, right, when you take the image of something. I mean, you can just see there are 2 degrees of freedom, right? So starting in 4 dimensions, one polynomial will reduce the degree by 1. So you get 3-dimensional thing. The common roots of only f1 will be 3-dimensional. Then if you intersect them with the common roots of another one, you should get a 2-dimensional thing. So by this time, you should have a 2-dimensional object, which should be this set. Or there should be some 2 polynomials. But there are no 2 polynomials which work, and 3 polynomials are needed. So it's a little strange situation. So it's an exception to the rule, to the usual rule of how the degrees, of how the dimension should decrease when you add more and more polynomials. It's an exception, but it's a very small kind of an exception due to very specific reasons, but we shall not go into them now. But again, you can try this exercise. You can see 2 polynomials will be enough. You can just even say it right now. YZ x minus yz is 1, right? One polynomial, you can think of another one quickly, and the 2 of them will be enough. And not surprisingly, as we have explained. And you can take other examples on your own and try. But this one is kind of a very strange thing. It's called the twisted cubic curve. Twisted. It serves as a premier counterexample to a lot of things. Well, I should not. I don't. Well, it's not a counterexample. Anyways, yeah, it's called a twisted cubic curve. These things happen all the time, so it's not really a counterexample. But when they happen and why they happen is also well known. But before we can study these things, one has to study linear algebra, where similar exceptions that happens in the case of linear equations and planes needs to be studied first. And that's the study of matrices and determinants, is just a tool that is used to understand those things. Okay, so we will see them a little later. So yeah, this was the thing I wanted to do. And so, okay, let's see if there are any questions. And then there was, what was the next thing? Okay, so just see if there are any questions. Yeah, so I'll probably take a second class in this week only. And yes. Sorry, I cannot hear you. Maybe my volume is very low. Yes? No, I cannot hear yet. You have to be loud. My volume is full. No. Yes, now it's better. Yes. Approach what? that there are no two polynomials? See, to find out the polynomials, you have to be constructive, right? If you want to actually find out. But maybe what you meant to ask is to show the given a set, let's say something like this. I tell you that, let's say S is sitting inside R4, and I tell you that, okay, and I ask you to prove that show that S can be written as common solution of 3 polynomials. Okay, then if your question is, do you really need to find the 3 polynomials, or is there some other way? Right? Something like that, no? Yes, so there is, yes, that's right. So there are some ways. So that's a very good question. So if suppose there is some set, it could be something like torus, whatever, some set. And this again can be written as a subset of R3 or whatever. It has to be in R3, of course. And so S, and then you want to say that show that S, show that S is the common set 0 of some 3 equations or 4 equations. Yes, there are some ways. So the way to do that is, so that's a little complicated. So what we have to usually do is you have to take the set S and you have to pull it back. So some set S, let's say, is given in R3. Then you have to, okay, so you have to take this set S here in R3. Maybe this is how I can say in R3. Then you have to think of some other set S1, some other set. So the question is this, given a set S in R3, the question is, are there polynomials? So forget about 3 poor polynomials, forget about the optimization question. We just ask the question, are there some polynomials whose common zeros will give you S? Or is there a polynomial? Let's ask a simpler question. Is there one polynomial whose common zeros will give you S? And you can always make, right? I mean, if there are 2 polynomials, oh, no. So 1 minute. Yeah, let me just keep it like this. The question is are there some polynomials whose common solutions is S? Just the question we are asking all the time. And if you want to give a non-constructive solution, if you don't want to actually construct them, or sometimes it may be not possible, so then yes, so then the way to do it is that you think of some other set S1. Okay, think of some other set S1, and let's say S1 is described by polynomials. Okay, so think of some other set S1 which you can easily describe using polynomials. Let's say some polynomial P1 and P2 describe S1, meaning the common zeros of P1 and P2 is S1. So common zeros of P1 and P2 is equal to S1. Okay. Well, this is also said as variety of P1 and P2 is S1, but the word variety is, that just name just came, it got stuck from somewhere. So yeah. So this is S1, let's say. Now, if you can mold this S1 to S in a polynomial way, okay, if you can polynomially mold S1, what does that mean? So it means that, so S1 is in R3 again, let's say. Well, it could be in other dimensions also, but basically you are viewing S, basically it means that you are viewing S from a different angle, and you are maybe changing the coordinates, angle between the coordinates or something, so that S now looks like S1, and S1 is a very obvious set. Okay, and this molding and so on is polynomial, meaning that, let's say that there are some polynomials, let's say psi1, psi2, and psi3, such that the image under these, so these 3 are all 3 variable polynomials. Psi1, Psi2, Psi3 are 3 variable polynomials. So if you have a set which is in R3, so it's a triples, right? The set S1 is made up of triples. For example, if you take a triple x0, x1, x2, and what you then do in the image is you write it as Psi1, x0, x1, x2, Psi2, right? And this will again be a point in R3. But if you can choose this polynomials in a nice way, and you can think of a easy S1, which you know can be described by polynomials. So if you can think of these things, usually thinking of one, you will know how to mold and so on. Some other intuition will tell you, hopefully. Okay, then you can say that S can also be described by polynomials. Can anybody guess what polynomials would describe S? So S1 is described as S1 is. So once again, let me say the entire thing again. Okay, S is some complicated set. Okay, I don't know what set. S is maybe some complicated set. So it could be like the surface. Yeah. So usually, actually, these things don't work in R3 very well. There is a problem. It should be C3 because then all polynomials have solutions because every polynomial in 3 variables has roots and so on. But we are just doing it R3 just to see. So what I'm saying is not completely precise, but conceptually it is not incorrect. Yeah. So what I'm saying is, let's say this is SS. S is some, look at this, some very complicated thing. Okay, and these actually have real applications, but I'm not going into that because we need to know more about manipulating polynomials. But arbitrarily, you try to understand in general. I mean, S is this thing like this. Okay, and you want to ask if can I describe S using polynomials? Okay, is there some polynomials f1, f2 such that the common zeros? Okay, so the question is, that is a very interesting question. Yeah, is S, so okay, 1 minute. Let me say it just in terms. Are there polynomials, obviously in three variables, polynomials f1, f2, f3, such that common solutions, so you must understand what this means, right? Common solutions of them equals S. This is my question. Okay, this was the question. Then we try to come up with a S1. Now that S1 may be just some simple plane, which we know can be described simply. That is the magic. Okay, we think of some plane, and then we mold it polynomially to get S, which means I think of Psi1, Psi2, Psi3. That's what it means. A function is just a renaming machine. A function is not a machine that takes an input, does some operation, gives an output. That's one way to look at functions. But in mathematics or in abstract things, a function is just a renaming machine, right? It's a renaming kind of thing, right? It renames the points in S1, this plane, everything in this plane kind of goes and maps. Okay. Now, if you can think of this S1, some simple S1 usually, which is a set of this type, meaning that it is the common zero of, let's just take one polynomial, forget about two polynomials for the time being. That is just an easy extension you can do. So let us just think of one polynomial. Let's say S1 is common zero of something. Okay. Some P. And you can think of a function from here to here, which is polynomial, meaning the Psi1, Psi2, Psi3 are polynomials. Obviously in 3 variables. Okay. Then if these things happen, if S1 exists, such S1 exists, then we can say S is, then we can say yes. Then we can say that yes, S can also be written using the zero set of a polynomial. What polynomial should that be? Let's think about that, or maybe oh, wait. I made a mistake. No. I made a very big mistake. One second. This will usually not work, but I'll fix it. 1 minute. So you are asking if S can be written like that. No. So no. Why would you do this? Sorry. You do the reverse. You mold S into something simpler. And you know that S1 can be written. So that's everything else the same. I've only changed this. Okay. The question is again, can S be written? So you simplify S to S1 using these polynomials. So maybe you stretch the thing. So the stretching is like polynomial. X is going to X square and so on. And now if you know that S1 is the zero set of P. Yeah, so for S1, this is zero set of P. So S1 is, then you can say that S is also zero set of something. And that is very simple. What should that be? So yeah, let X0, X1, X2 be in S. Okay. Then you consider this psi1 of X0, X1, X2, psi2 of X0, X1, X2, psi3 of S0, X1, X2. Okay, this is an S1. Yeah, this is an S1 because that's the thing. We have stretched it to a simple set S1. But this vanishes at P, which means that P of this is 0. So now do we have a polynomial that kills X1, X0, X1, X2? A 3-variable polynomial? Yes, it is simply P composed with psi1, psi2, psi3. This will also be a polynomial in 3 variables, right? So remember, P is by P I mean P of X, Y, Z. Some 3-variable polynomial, right? P of X, Y, Z. And in place of X, you write psi1 of X, Y, Z, psi2 of X, Y, Z, psi3 of X, Y, Z. In place of Z, you write psi3. That also becomes a more different polynomial, right? In 3 variables. And that is exactly killing the points of S. Right? Well, so in some sense, you have actually found the polynomial, but that is if you know that the exact polynomial of P. But you see, we did not need to know the exact polynomial of P. We are just saying that if there is a polynomial P which kills S1, then mathematically, we know that there will be a polynomial which will kill S. Obviously, there are some still checks to do that there are no extra points and so on, but you can check it. That if something kills P1 or P0 of psi1, psi2, psi3, then it also kills S and so on, so on. You can prove inverse image. Okay, so it's the exact thing. So this is one way. Basically, so the idea is that you have some complicated set and you use some polynomial equations and you simplify it maybe to a circle or a parabola. A parabola is killed by a polynomial, right? Y minus x square. An ellipse is killed by a polynomial, right? Something like this. So some other complicated shape, you apply some function, you apply some polynomial functions to it, and you can make it a simpler. Yeah. It is a polynomial transformation. Yeah. The only restriction is that these must be polynomials. Otherwise, this will not end up being a polynomial. Okay. All right. Okay, then. So let's stop here today. The problem I plan to discuss, maybe we can discuss next time. Okay. So, or maybe I'll just discuss it tomorrow only. Okay. So tomorrow we will continue with the partial order thing. Okay. And yeah, there also we will. So tomorrow we will do some supremum, infimums, and so on. Okay. So we will do it there, and I'll discuss the problems. We'll discuss. Okay. I'm feeling a little sleepy. Okay, then. So let us.